Up the volume there a little bit. And, yeah, there we are. Welcome! Hello! I'm Agent Ultra. I'm going to be here to hack on some Haskell for the next couple of hours. We work on little practical things here and there. Sometimes we're impractical things. We're just learning stuff. Sometimes libraries and whatnot. This week we're going to be digging back into the wave function collapse visualizer that we've been writing as a front end, a visualizer for the wave function collapse algorithm we tried implementing in Haskell to see if we can learn about that algorithm and stuff like that. And I think if we have time, I might work on some other libraries. Excuse me. I got a database client library for a database called Tiger Beetle. We're trying to write in Haskell, so I might work on that. We'll see. But for now, let's just kind of dig into the code and see what happens. See where we go today. Oh, I'm going to take this out because I don't actually use this microphone. That's for work. And it's not work time anymore. Okay. So, when last we ran this, we got it to display our input image. This is a good amount of progress here because for a while there, we had to do some like pixel format conversions. We were loading an image using SDL's image library, but then we were loading the pixel data into an internal data structure used by the algorithm, and then trying to spit the pixel data back out from that internal structure once the algorithm was done, and put it into a SDL texture, and then render the texture. That took a while because of like some pixel format conversion stuff, and offsets and things like that, a bunch of low-level things, but we got it going. So here we are. It's now going into our texture data structure, and then back out into an SDL surface, and being rendered again. So we know we can get data into our algorithm and back out again, and it renders the same. So now my goal is to hook the algorithm back up and see what we get as output. Let's open up the code here. We're going to go into app. That's like the main for the executable here. And so to surface, from surface, all that stuff. That is what you would have to write in order to use this library. Maybe we should, like, if we want to actually package this up as a library, I don't know, include some of that code. I don't know. So other people can use it. Maybe. However, this stuff is what I want to get going. Again. We'll uncomment this region. Alright, so we don't need the app loop here anymore. Or this image texture. Or this image texture. I think we get rid of that. We load the image. Alright, this from surface turns it into our wonderfully named texture data structure. Okay. And actually, I'm going to keep some of that because I got to pass the pixel format through somewhere, don't I? No. No. Okay. What am I reading? Comment this. Okay. So we get our input texture in our pixel format. Then, yeah, we need the pixel format for the to surface call when we go to render this, which is down here. Okay. Pixel format, boom, there. Okay. We get the pattern results by cutting up the input image. So that input image we saw there, the algorithm, like, we're using what's called the layered tiled approach, where you like kind of cut up a small section of the image and like a little card of it, and then you move one pixel over and cut another same size card over and another pixel over and so on and so forth. So you kind of get overlapping cards or tiles or patterns as we call them here, overlapping patterns from the input image, and that generates, we use that to generate the rules that are used in wave function collapse. So in the second phase of the algorithm, right, we create the input wave state, we get an output state wave state. So in the second phase of this thing, we run the wave, and we do that by generating these rules from the input tiled images source. And the rules are basically like which of those tile sets are allowed to like overlap with each other in each direction. Right. And that allows us to then generate an output image, a much bigger one. Right, that's going to have locally similar features to our input image, but it's going to be kind of randomish. And this is useful for all kinds of things, including textures and images and whatnot. So we take the output state. If we don't get an error, then we have an output wave function collapse texture. We're going to just put that. We're going to output WFC texture here. So our output wave function collapse texture with our pixel format. To get our surface image that we're going to render back down in SDL to the window. We get the image texture there, so we create a texture from the surface. And we pass that into our app loop and just display it until we quit. That's our program. Cool. Okay, let's see that. Let's run our builder. Let's run it optimized. We'll use the file launcher. So we'll create an optimized build, just so it runs a little faster. We've got some cleanup to do, but that's okay. This is just learning code. Maybe, I don't know if we'll make a library out of this one. I might want to, if I actually do want to make a library out of it, I might rewrite the code, try a second time. But that's how you learn, right? At least that's how I learn. Okay, let's try it out. Let's see what happens. Takes a little while. It's not terribly efficient. It just works, hopefully. Let's see what we get. Make sure I got chat up here so I can see you, beautiful people. Oh, okay. We got some issues. T-cache chunk detected. I have not seen that before. Unaligned T-cache chunk detected. Interesting. Do a little Googling on that and see if that just was a fluke, maybe? What was the error again? Unaligned T-cache chunk detected. Okay, like a buffer overflow. Okay, corrupt overwritten something. Oops. Okay, so we tried to allocate something. We'd actually overwritten something probably. Interesting. Okay. Possible bug. Probable bug. Okay, now we got a black screen. That's not quite right, is it? Yeah, maybe it was a fluke that time, but, okay, now we're getting black screen. That's no bueno. Okay, so we'll probably want to check, obviously, the output data, and then we get a segmentation fault. Okay, it wasn't a fluke. Something is up there. Do. Okay, it could be that we do need to actually lock the surface in order to write the pixels. I think we do, but maybe we missed that. peek, raw format. Yeah, maybe that's our problem there. Okay, let's look up the SDL library for the lock surface. Surface. No, should be another one. Set up a service for directly accessing pixels. So between calls to lock and unlock surface, you can write to and read from surface pixels using the pixel format stored in surface format. Once you're done accessing the surface, you should unlock it. Okay. Not all surfaces require locking. If SDL must lock surface evaluates to 0, then you can read and write to the surface at any time, and the pixel format of the surface will not change. Okay. If we go to surface, do we lock it up in here? We do with bracket. We bracket with lock surface, unlock surface on the output there. So like we get the surface pixels, gas pointer, but it also said read in there, I think. And read from surface pixels. I don't know if that matters on the read side. But it's not too hard to add that. So let's do that here. Just to be super duper sure. Unlock surface. Pop all that stuff in there. Okay, boom. It's probably not going to fix the black pixel, black data area, maybe. No. Hopefully the other issue goes. Away. It'd be hard to reproduce something like that, so I don't know. I think I'll commit it anyway. Nope, there we go. Unaligned T-cache chunk detected, so it didn't. Okay, so we're totally allocating something and overwriting somebody's memory. Gosh, where would that even be? Okay, we're gonna dig into wave function collapse code here. We do use a fair bit of arrays, but I don't think we use any foreign data. One thing that could be happening, well, when we go to set the SDL surface from our texture data, could be that the garbage collector is collecting in the middle of us setting things. Maybe it's a garbage collection issue. Because we call, let's see, here, to surface, output texture, so we still have a reference to it here, and we call to surface. So I don't know if it's that. But we can print our output WFC texture to see if we're getting any data in it. If it is somehow internal to our thing, then yeah, we'd get the underlying tongue detector before this, I think. So all zeros. Not what we're expecting. Yeah, that chunk thing comes up after. So I wonder if it is something to do with the way we're allocating the surface and writing to it. Maybe we're writing out of bounds. And we're not calculating the size right. Let's print. Just the tuple there. Let's just print that. Okay. Because our output image should be bigger than the input one. We're saying 1414. So at least it's square. That's correct. We're not getting any bad data accesses there. But still, not what we're... Well, we're still getting a seg fault there when we quit. Interesting. Okay, if we go into wave function collapse, we initialize the wave. Init state, we run the wave. Make wave state. Okay, there's a desired grid width and height. And a pattern result. We have the frequency hints, adjacency rules. We create a grid. Pattern results and frequency hints, adjacency rules. Well, we create the patterns. I think we're pulling out the data out of the texture thing, which should be just like the untouched raw pixel data. And we know we can go into a texture and back out to a texture, from a texture to a surface, and render it fine. So it's got to be something in here. Grid width, grid height, pattern results, frequency hints, and adjacency rules. Standard generator 850, right? Okay, so this then this one runs it. Yeah, that's everything we need to create this state. Our output texture. Yeah, let's check our output. Are we using output texture? Gotta be using output texture. Let's see. Make output texture, pattern results, the output wave state. Okay. So we get the patterns. Oh, okay. Let's see here. We're constructing a texture in the pattern pixel. Patterns. Okay. This could be maybe a potential area of bad data. What do we use that for? Pure texture. Okay, so assuming we get the pattern indices and the patterns, then we're constructing a new texture in here. Right, because we get the... We're supposed to chop up the patterns from the input image. Right, those little cards I was mentioning at the beginning, they kind of like slice it up. And then when you're constructing the output texture, you only take... When the algorithm runs, it's only placing the indices of the different cards. Like, it's just saying, in this particular location in the grid, place this card here, and then based on the rules, it's going to like eliminate a bunch of other cards from other places in the grid as it goes. Until we flatten the whole thing down so there's only one pattern per cell in the grid. And then the pixel you're supposed to get when you generate the output texture is just the top left pixel of the pattern. Right? And then we put that into the texture, our output texture, on the bounds that we want in order to create our output. So in constructing this from here, we get the pattern pixel. And there might be some step in here where we can't do anything with the pixel values once it gets in here, because it's all texture A, pattern A. But when it's getting to the output, they're all zeros. So let me actually check our pattern results. And see if we're slicing things up right, if the patterns have reasonable looking values. Okay, not looking handy so far. And there's an invalid pointer now as well. So something is definitely getting... We're holding a reference somewhere or letting go of a reference of something that we need. I assume the bracketing on the SDL surface would have handled that. But maybe it's something internal in the library. Okay, so these patterns... Right, 1 1 0 1 1 2 2 0 2 1 2 2, all zeros. That's a sign there that that's not quite right. As if you get the top left pixel of 0, and it's just going to be 0. And we're going to get black. Yeah, I think they're all zeros. So something's up with the pattern cutting stuff. Okay, so let's take a poke at that. Let's create a little commit here. Oh, right. Phew. Got the silly setup. This VM has kind of worked in some ways. That. I've just never fixed it. I always like mean to. I'm like, I should fix that. And I'm like, eh. One of these days, I'll stop being lazy about that and get it fixed. Anyhoozle. Right. Let's get back to where we were, which was creating our committee commit. When applied, this commit will enable the algorithm, the visualizer. Okay, so let's see if we can't figure out what's wrong with this now. Okay, so in main, we call pattern results to get the patterns that we use as the input to input wave state to construct the wave state with. Pattern result is that structure that contains those things. Oh, okay. Now something else on the computer's messing up. It's power tools again. It's decided to turn the caps lock back on. Cool. There we go. So the patterns function. That's where we are. Input texture A gets a word, pattern result. Okay, so the word is the subpattern size. Okay, we extract a pattern from the texture subpattern size. X is 0 up to, Y is 0 up to. The elements we get out of the texture elements. This function here, fold accumulates from tech some indices, add some indices. We get an index, and we index into the texture array, add index. So it could be that our indices are just way off base here. Possible. Okay, so let's now make sure that the input texture we get here actually has not been touched and has the data in the input data in it. We can go just debug.trace that here. And we'll go patterns. Let's show here. Yeah, we'll just import debug.trace up here. Qualified. res. Debug. There we go. All right. Get our builder going again. We got a problem here. Ah, right. We can't show it. Oh, because we don't have a show. Okay, yeah, we just have to add that up here. Perfect. Okay, so we're gonna get up here. Run it. Okay, so it looks like we do get data. Possibly correct data. So it's definitely that function there that's extracting the data out into those patterns. It's like getting nothing and doing b-ball. Might even be the source of our site faults, but maybe not. But could be. Why would it be though? Hey, I don't have a good idea why. It's just a guess. Okay. Okay, so let's see. We call extract pattern with x, y. So x and y are going to be x and y. So, so the solipsism. They're like they're independent of each other. They're all the like the 2D coordinates in the texture, so to speak. Okay. So at extract pattern, we take the tuple of these. We get a texture, a tuple, and a size. All right, we get the size -1. We get the indices here. What are we doing with these indices? We're going, oh, because we want the sub, we want to extract the sub, a bunch of the pixel data to put into this pattern, to construct this pattern with. It's ultimately what we're returning here is a pattern. Okay. Pattern is an array. Up to the width size. Okay, would there be a problem with accessing these randomly? From the texture? I don't think so. But clearly when we go to accumulums, whatever index we're computing here is not right. Show the index here. And again, I took the A off, the show instance off here, we'll put that back on. I'll probably get rid of that. All we're getting here is 001020, 01, 21, 02, 1222, 102000, 112101. over and over and over again. Okay, so that makes sense. We're basically filling it with a black pixel, but we're selecting the same square for every pattern. It looks like that we're trying to cut out of this thing. Okay, don't we have some test for that? Okay. Property is the sum of subpatterns. So we check how many patterns we cut out, and that's apparently correct. We get, given a subpattern from the 0, 0 index of the source texture, this supposedly gets... Apparently I did a lot of debugging here too. I think this was a lot of streams ago. We worked on this a little bit here. So the pattern indices should coincide with source texture indices. What are we checking here? That is, we take patterns from the texture of size 3. We call pattern result patterns to get the patterns out. We take the head of that. The first one we get in that list. So maybe not necessarily the 0, 0 pattern. Pattern indices. And that's the array indices of pat.getPattern, so the internal array for the pattern. Texture values. Get value from texture. Value text patterns. Why do we have to reverse that? I don't remember. And so get value texture t of these. X is t array x of these. So we're saying the texture values that we select should be the same as the elements of the array, the values, in the pattern. Okay, that all looks fine, but our current problem is that we are trying to get more than one pattern from it, and we're getting the same pattern every time. So we could, perhaps, and should, write quick little tests to make sure that we're doing that properly. Okay. Let's get rid of those. Let's just clean up this code a little bit. And then I'm going to add another one. Given an input texture. Like this. It should return distinct patterns. As long as the input texture that we are using is capable of providing that. So that means like we don't have a texture of just zeros, right? Otherwise this wouldn't hold if that was the case. I think this example at 3.3 size should do that. 2, 3, like that one, would be different than the next one we select, which would be this one. And this one, it's going to wrap around to get 001, so it'll just be like, yeah, that'll be all different. Yeah, that one would be different. This would be different than what we've seen before, so... I think we could say that all of the patterns that we get after cutting them all out from the input texture aren't the same. At least for this particular example. I think that would be true, although we have to be very, very careful about this input example that we don't tricking ourselves here. I believe it will cut here and take the top row from above, creating a row with 111s at the top, which this one would also have, but in its second row would be a little bit different because the first column would be like 1111, and this would be 100, so that would be different. Yeah, I think that should be true for this example. Let's grab that. Now, we get all the patterns. How do we say that for each pattern it's not equal to any of the other patterns? We could just create a set from them as long as there is an ORed instance on it, which I don't think we have because the A... Let's see. Oh, we do have an ORed instance on it somehow. Okay, so we should be able to create a set out of it. Let me make sure I got that in package. Dependencies, containers, tests, containers, good. So... distinct patterns should be, if we set from list, oh, we gotta get the patterns first. These. Get the pattern result patterns of volume patterns on tech size 3. Now, distinct or unique patterns should be something after from list. I think P is a list, but maybe not. Gotta import that. Import qualified data.set as set. Get our test runner going. It's fast on this one. Anyways, I think we're just going to do set.toList. We just use nub there, but whatever. I don't know. And then we basically should get keys should be unique patterns. I can call this like maybe all patterns. That might be a better name. That might not necessarily be true. Might just fail just because of list ordering stuff. But let's get the basic bits out of here. Yeah. Okay, so we should sort these. Well, we can't sort on it. What did I do? Oh, it's just not scope. Okay, let's get going. All right. Okay, here we go. We're compiling a failure. Awesome. Okay, yeah, so we got one pattern, two pattern, three pattern. We start differentiating a little bit, yeah. But one thing I'm noticing in test, though, at least, is that this one's actually pulling out values. All right, 0, 0, 1, 0, 0, 1, 1, 1, 1. Which is different than what we're seeing in production here. That's no bueno. Don't like it. That's 0, 0, 0, 0, 2, 1. And we've got 1, 0. That's there. That should be 1. No, sorry. Yeah, no, 1, 0, 1. Okay. 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 Yeah, something fishy's going on here. All right, 0, 2. That should be 1. That is. 1, 0 should be 0. And it's 1 here. So yeah, something be fishy in the land of indices once more. Hmm. No, no, no. No, no, no. No, no, no. Something is fishy here. These array indices are not our texture indices. These are the indices in our pattern. So this might be perfectly fine, this pattern here. Sorry, the first one we get. Are expected. Well, obviously, well. It's possibly right. Assuming the prior test is correct, then I think this one is also... That first one is fine. Okay, so why are we getting... Yeah, so we aren't... I think for the one slice we're getting something right there. Okay. This X and this Y at this level in patterns at the top. Up to is our texture size. We know it's square, so each of these is going to be the same. So I think that makes sense to find that once. So, for example, we want to go from 0 up to 2, inclusive, or up to 3, uninclusive. And that's, so this is to go over every element of the texture. We've done this before in main. I have to go with width and height minus 1 there. Yeah, so it's width and height minus 1. Okay, so I think that's probably fine. And we call extract pattern with the combination of those two, x and y values, and our subpattern size. Okay. Passing the texture through. Extract pattern. So what does extract pattern do? Gets out tech, gets the x, y position, the coordinate, and the size. Okay. Because we're going to be accessing the array in tech. Tech is an array of word A. Okay, so our XY is going to be the top left corner of this pattern that we want to extract out from the texture. And so our indices need to be greater than that value. Or if they wrap around in a torus, then they could also be less than. Which I guess is why we're using mod here. So we take A to be our X, our top left column, and add the up to X plus width. We wanted size 3, then we're going from 0 up to including 2. Same for B. If that's 0, then we go up to including 2. And then our texture elements, it's this fold of all those indices we generate. When we take B and A, we mod them by the size. And why do we call them B and A? Well, obviously to not shadow X and Y, I guess. We're passing them in the other order here, which we've also seen before. When we wanted to get things out in row order. And put them back in row order. We had to sort by the Y component there. So maybe these should be flipped. Alright, so look at the B mod size. That might be 0 mod 2, which is going to be 0. That might be just like a safety, I guess. Texture elements. Now. The indices we're generating here are going to be up 0, 0 up to. Okay, we're generating the array from 0, 0 to width, width. Okay, and then when we accumulate the elements from texture, we're hoping to get these indices to be in the texture's coordinate space or its index space. But when we were doing the debug, we saw it just repeat the same pattern space over and over and over again. When we were going to accumulate elements. Which means X and Y probably weren't changing. Mm-hmm. Get rid of that. Okay, that made that, oh, an exception. Yeah. So the mod was there for a reason. Right, because, oh yeah, the mod is there for a reason because we can go X and Y up to the very edge. That's the test. Right, so we could extract like this column here, right, X3, and we still want to get X0 and 1 as like the next two columns if we're extracting a 3 by 3. The modding by the size layer 3 would get that. What is texture elements there? Let's debug that out. Why can't we show it? Oh, that's no problem. Right here. Probably here as well. Just anticipating things. You never know. Okay. Well, this one's not turning right anymore, so that's... I don't know if I broke that in our current excursions. But that's something. And then the other bit here is that our fold is just getting all these zeros here. What have I changed? Just type signatures. Well, I flipped around the indices there. Okay, so let's get rid of that change. Add this back in here. Add this back in here. Yeah, it's a little different. It's good, at least in the test. We're getting... See, we're getting data there from extract pattern. We're just getting zeros on our input. What does that mean? The texture, the input texture, when we get it here, I should have plenty of data in it. Oh, I didn't finish building, I guess. Yeah, clearly we're getting the input texture is being passed in with data. So we should be seeing non-zero data here in the, at least in extract pattern here. Some of these. Okay. So the texture when we get to that point is definitely fine. Our input texture under test is fine. And extract pattern from that is actually working. What's happening here? Let's dig a little in and maybe pattern size here. Let's show tech. Okay, that array populated with the data. 0, 0 to 11, 11. Okay, let's print out our indices. Okay, it's gotta be our indices then. Like, look at this. It's all the same over and over again. Okay, so I'm doing this code's doing something really dumb here. This code is not correct. It's always giving us the same ones over and over again, and just different combinations of them. Never going above 2. Makes sense because we're modding. The result, those values by the size. That's subpattern size. We say is 3. Of course it would never go over 3. Hadar. Hadar, hadar. So then, yeah, that's kind of silly. That's not right. We wanted to mod over the width of the texture itself. No. Texture, the texture size, the width of the size of the texture. Come on. Okay. Texture size. We got a function for that. Equal NT. Text size. Text size. Only one failure. Skadoosh. Okay. That might be our expectations wrong in that test now, but it's not using a very optimized version of the build at the moment. Going a little slow. I wonder if we get that test to figure out what's up with that while we wait. This one up here, not what we expected. Kind of curious why we had the fold in there, or that reverse. There. We were compensating. Okay, that's just gonna be too slow. We should probably just run the optimized one. Stack build. Turn that back on. Okay. Are we Pac-Man yet? Might still have pointer errors and junk stuff like that. Come on. Getting nothing so far. I don't know if that's a good sign or not. Maybe it is. No Malik problems yet. Oh, that's our big chunky overlaps function. Checking if a pattern overlaps another pattern in a given direction. Oh, still going. Oh, still waiting. Okay, let's go surf the internet, I guess, for a bit. See what's up in the Haskell space. There's a Tokyo Haskell meetup. That's awesome. On the joy and occasional value of linear comonoids. Comonoids. Arnold Spelak. GHC contributor and maintainer of linear types. Cool. That's a mouthful, I gotta say. Create a table with raw query. Cool, cool. Advent code and Haskell. We did a little bit of that. I didn't finish all of them. Okay, I don't know if we're making progress here. Oh, where'd everything go here? Boop, boop. Oh, hang on, I lost chat there. Get you back, chat. Cool. Gotcha. All right. Let's see. Yeah, Bing W. That's not that interesting. Where's our output? Still waiting. Okay, so we're hanging on something maybe. Interesting. I gotta give it a few more seconds here. Announcing Aztec 0.2 and ECS for Haskell game engines. Now faster than Bevy with a new simplified core. Check it out. Performs past as competitors. Uses archetypes to directly store groups of matching components together. And tightly packed sorted lists, allowing for super efficient queries by entity ID. Cool. That was a game dev Discord. There you go. Check it out. Hopefully this font is big enough for you. Aztecs 0.2 ECSs. So it's like a entity component system. It's just an architecture for setting up data that is frequently updated a little bit at a time, like subbits of it. So you access it, you set up to be accessed and read frequently. Cool. Yeah, I would like to check that out. Let me follow the GitHub link and give it a star. Create a position type, a velocity type, instance of component for position and velocity. Oh, it just derives it? Interesting. Access of IO of unit. Spawn an entity with position and velocity components. We got 0 and 1. Update all the matching entities. Create a next state. Oh, interesting. There's another library I use that has this same syntax and does similar things where you have to like match out the whole structure. Run access app wmt return unit. Aztecs is currently faster than Bevy ECS, a popular and high-performance ECS written in Rust for simple mutating queries. What? Query 10,000 entities, Aztecs, 932. Oh. Interesting. Is it the data structure that they use? I mean, you don't typically hear that kind of stuff, that like, this is faster than Rust when it's written in Haskell. Interesting. What's flex? Fast and lightweight entity component system. Oh, it's just another one they base theirs off of. Okay. So I guess this one did a fair bit of the work to set up this data structure, I guess, that they use. Interesting. Neat. Glad I gave it a star. I'm going to try it out for my next project, see how that goes. Thank you so much. Okay, let's check on our thing. Okay, it looks like we're probably hung. Looks like we're not making any progress here. No malloc errors here, any seg faults, but I'm just gonna like interrupt it here. Okay. Let's just do a full stack clean and build. I don't think that's really gonna change a whole lot, but it's getting hung on something. It means it's not able to finish. I mean, if it's still making progress, but it's not able to finish, or it's getting stuck in a loop. Thought we added some potential assertions in there to check for that. Yeah, let's kick off one more. Move to the side here, and then we'll just do a little investigating, a little poking around. Okay, modify cell, push removals, get the neighbor removals. Okay, propagate. This will be probably our main area. When the enable count equals 1, when not, contains 0 count. And we can modify the cell, find a contradiction, then we should throw an error there. Now, it's really hard to detect in most programming languages that are proof that, like, good things eventually happen. Right? Like, eventually we should end up with an empty removal stack. We're just missing temporal logic, really. That's all it is. We just don't have it in the Haskells. We can't tell if basically we can't tell if our propagate thing here is going to finish or will eventually finish. I wonder if there's another like kind of side channel way we could figure out at least something that's like something's funny, you know? Like something might be going in and adding new neighbors to our stack indefinitely, and that's why we're not making progress. And we're not finishing. Maybe in our decrement neighbor enabler counts. What do we do here? Pattern index, a pattern enabler count. We take a direction of grid cell. We either return a string or a grid cell. Right. String? No, this is returning a cell. On the left. Oh, it's let cell. Okay. That's kind of a weird function. I'm sure that's probably because at this stage in the code, we were looking at the Rust implementation that we found that had like some weird funkiness to it. We could have copied some weird funkiness or just not implemented it properly. But cell enable accounts, if we do update these, oh right, because grid cell we made left, we also made like an alias around either, which is why we have cell at right and cell and left cell. So right cell is a purely collapsed one, I guess, and left is like not collapsed. Okay, that's why the left here. That was confusing me. That's super confusing. Why did I do that? I don't know. Maybe I should have used some fancy types for that. But... okay, it's coming back to me though. So this is just the next cell state. And so the counts, here we update those counts by the pattern index, decrementing the direction from enabler counts direction cell. So our cell and pattern enabler counts should never go below 0, for example. That would be silly. Yeah, that's not making progress there. So we could just add a little assertion there to make sure that that's true. Okay, so let me just pull this. Pull that up there, that there. Okay. How do I want to do this here? Well, we can return either. We're returning just a straight right here, but we could return the string actually. If something about the counts, then actually return left. Counts. Else. Okay, so our pattern enabler counts is an array. So all of the elements of that array, looks like the values are the counts. So something about those. Must be true, read all of them. Or any something fail, any of our function fails, whatever our function is, over the array elements. of counts. And I will call where that is negative count. Something like that. Plop it in that hole. The type can be wrong, but GC will tell me what it should be. I can fix that. Implement it. Pattern enabler count to bool. Very simple. Okay. Pattern enabler count. There it is. It's also an array of integers. We'll get those out, that array out here. Okay, we can again take the elements of that and we can say and all greater than 0, greater than or equal to 0. Something like that. Uh-huh. There we go. Okay, so the neighbor counts are getting decremented below where they should be. Below 0. Somebody somewhere is getting decremented inappropriately. What does that mean when that happens? We call it modify the cell at the neighborhood coordinate. We call decrement enabler counts here. I think. Yeah, that's the only place we actually call it. Yeah, we call it for here for each compatible pattern based on our adjacency rules. The remove pattern, one that we just removed. For each of those compatible patterns, the enabler counts. On the enabler count, and there is 1, 2. It doesn't contain 0 count enabler counts, so we do this. Unmodified, decrementing the enabler counts. I wonder if we just need to push that in one level. Okay. Hmm. So we're still getting that, even though we push it in here. We get the enabler counts for a particular direction to be 1. Okay. Which means, I guess, we're not guarded by this condition here that it's non-zero enabler counts. Maybe it just needs 1 more? No. I think we're just gonna have to, like, call bankruptcy on this approach and try this again. Because, good golly. It's tempting. It's tempting because I haven't seen it in a few weeks, and I haven't been looking at it in like a month. Yeah. I thought maybe we were good, at least on the algorithm side of things. Maybe like perfect, but it would at least run and finish. We had a test though for that, I think. Maybe we messed something up there because it used to. I think it used to pass. We had like a kitchen sink test. We're still getting 1 failure. And it's the kitchen sink test. And it's failing on the neighbor counts assertion that we just added. If we flip that back. Okay. That small example succeeds. Somewhat. Our kitchen sink test doesn't test that it generated the right things. It's supposed to be somewhat random. But just that, like, that we made progress. That's all it tests. That we end up with an output grid that is sufficiently different from what we started with. Which isn't saying a whole lot, right? Because you could change just one element of the input or the test, and then that would be enough. Right. Start with an input texture 4. We get the pattern results 3 here. We start with a deterministic seed of 100. We have the wave state with our set seed. Pattern result. And we get our final wave state. And yeah. Then we have that here showing the pattern results patterns. And now we check that the init wave state that we started with for the grid is not the same as the final grid. Right, so if all this run did was like change one cell, or the state of one cell in the grid, that would be enough. So it's not like super great, But like it was just to give me an idea that like we're headed in the right, somewhat direction. So it could just be an efficiency thing. It could be that this is just so terribly slow and bad that we're just not ever making progress. Or we're making progress, but we'll eventually finish. It's just going to take a long time to get there. More time than we have to be on the street, which sucks. One theory we could do to check that is we could just look at the stack size, I guess, of the wave function and see if it's growing. Or like if it gets down to like a small size and then grows too much and then like just never finishes. That could be an indication that we're running in loops with our propagation step. We pop the stack. We'll get the debug stack here. We called it the removal stack. No. Wave state remove pattern stack. There we go. We're in a state here. Have to debug that. Stay right there. Now, in our test, we should see the stack initially. Like it gets empty at there. Should see it fill up a little bit. I go past it. On the test. Never grows any removals. Okay, interesting. But ours should. Although let me do a build, an optimized build for that. Okay. It kind of grew and then went to 0 and in one boom step it looked like. Boom. Boom, boom. Propagate index 131. Okay, and then we get to an empty stack. Then it looks like we're just infinitely staying at the empty stack. So maybe our base case? What's our base case? Propagating. Collapse wave. So remaining cells. If it gets remaining cells gets to be 0, then we should stop. We got a main. How do we run that? Collapse wave is our function. Yeah. Collapse wave. Okay, so our remaining cells would be getting down to 0. And let's drop trace here and see if that's getting updated. Collapse wave. Show wave state remaining cells. Okay. Ooh, running low on time here. I was hoping to get to the Tiger Beetle client. Okay. No, it's just to show that. There you go. Wave state remaining cells. What does not have a show instance? Oh, it thinks that's the function. Sorry, I was passing a function there. There's no show instance for functions. I meant to show remaining cells. That's how you know we're getting to the end of the stream. Collapse wave, 225. Looks like we're not even hitting collapse wave again. So something inside... Oh, grew the stack a bit there. A few more. Should probably take those out. Let's take that one out. So, like, the stack is growing and shrinking. Things are happening there. That's good. It's not infinitely staying empty, at least. But it looks like we're not hitting collapse wave again. And we go to collapse wave. Right, we do recursively call ourselves. 224. So it did call it again, at least once. 223. Maybe it is just ludicrously slow. 222. That could be it. It could actually be making progress, and there isn't necessarily an error there. That's really slow, though. I'm probably using really bad data structures and all kinds of stuff in places here, which might be the cause of that. So, can we at least, maybe we could just test this with like a smaller output size. Maybe it'll be okay enough for that. Let's take that out. Let's go to main. Alright, so that's our output size. That's our seed. Let's make an output size of like something ludicrously small, like 5.5. This might take a moment because we're so that was going like 1, 2. Oh, and we got a T chunk detected here. Core dumped. Okay. So two things. What's this output texture? Well, it's still got zeros in it. I'll have to remember where that one's coming from. Slowness. And I think I'm suspecting this malloc or something to do with the way we're allocating the SDL surface there, or modifying it. Yeah. Okay. So, actually, let me put that debug back in. So let's leave this at 5.5, but in the library, we still got to collapse to 25. Actually, if it's 25 and it was like only like a few, like maybe 30 seconds before we encountered a crash, then yeah, there's definitely some kind of memory access or allocation we're doing. It's kind of weird. Okay. It collapsed and finished, at least at that size. So yeah, the size of our output really drastically affects our performance. It's incredibly slow on larger things, which is no good. We're still getting black pixels. I think that texture we're printing output WFC texture, yeah. So that's the output texture there. Maybe not in the patterns anymore. If we go back to here, print out the pattern results. Okay, so our patterns now are starting to pick up data, which is good. But we're still ending up with black at the end, so there's another step somewhere. Similar to patterns where we're indexing out data from the texture and we're not getting the right stuff, and we're constructing something new with junk. Probably indices. Always indices. Okay, but we're out of time for this week, so we'll have to put that in our to-do to fix. Wave function collapse. To-do. That's all working on the visualizer side of things. Now we have bugs. Pixels and what up? Too slow. Okay. Let's push up what we got here. Okay. We'll call it fixed pattern. That's all right. So, if you want to check out the code for whatever reason, maybe morbid curiosity, you can find it on GitHub. I'm Agent Ultra. And you can find it on github.com at Agent Ultra. That's me. At wave function collapse. I'll paste that there in chat. Boom. Boom. Alright, if you want to find me on the Fediverse, that's basically the only social media I really use these days. I'm Agent Ultra there as well. So you can find me there. It's got links to everything, including my website, which is agentultra.com. So you can go there and find links to everything there as well, including my YouTube channel where I back up the VODs for this stream. In case you're a first-time watcher and you want to go back and watch some old stuff, I don't know. But thanks for hanging out with me. Thanks for following along, and I hope I'll see you next week. I usually do these streams on Tuesday evenings at 10 after 8 in the Eastern, I guess we're in the daylight time zone now. Whatever. And you can write that down, or if you want to get the notifications, you have that all set up on Twitch, just give me a follow here, or a thumbs up, like, and subscribe on YouTube. And you'll get notified there if you're watching from a different time zone. So thanks again. Go to the link above my head. You'll find other cool streamers doing cool programming streams in different programming languages, as well as a link to a Discord server that has a channel for this stream here. So if you want to talk about your projects or whatever after in between streams and so on and so forth, you can reach me there and hang out. That's it. That's all I got for this week. So mail your monads, be free, and may your types always check, and we'll see you next week, where I think I'll probably work on the Tiger Beetle client, and maybe we'll work on this. I don't know, but follow me on the socials and find out, and let me know what you want to see, and I'll see you next week. Take care out there, and yeah. Let me end the stream now.